Welcome, ladies and gentlemen. Today we'll be talking about linear mechanics. Let's get it popping. So, a few different terminology bits before we get going here. So, biomechanics. Okay, bio meaning a living thing, mechanics talking about movement there. So, essentially, what biomechanics means is the study of forces and their effect on living systems there. Okay? So, essentially, we're applying physics here to human movement. That's important in exercise there because we, as human beings, living human beings there, we move there and we can study the physics of our movement. Now, in biomechanics, there are kind of two different subcategories. Kinematics deals with the description of movement using variables that refer to time and space, versus kinetics deals mainly with forces, okay, that cause change in motions there, forces there, and torques as well. And we'll talk about each of these here as we move on here in this course. So first of all, linear kinematics. So as we've talked about before here, okay, force composition, okay, essentially is just the sum of all the different forces that are acting on a system at the same time. Now we can't just add up all the forces there because the forces go in different directions. Okay, we need to consider the direction that those forces are being applied. Okay, essentially a vector sum. Okay, we'll talk about vectors a little bit later on here in this PowerPoint set there. Now net force. Okay, again, is the sum of all the different forces there. Okay, we can also call that as resultant force. So essentially, it means the same thing. Take all the different forces in a system, add them together, okay, although not an algebraic sum there, they'll give us a total amount of force there in that particular system. Now, as we talked about before there, in order for us to have an acceleration, there must be some sort of net force that is occurring. Okay? So if the net force is zero, okay, acceleration is zero. Okay? So on the flip side, there is if there's an acceleration, there must also be a net force. Okay, so there must be some sort of force moving something in a certain direction there for us to have an acceleration there. So any non-zero net force, whether it be positive or negative, there will result in an acceleration. Also understand, remember that just because no acceleration is occurring does not necessarily mean there is no force there. We just know that there's no acceleration that's happening, but forces are occurring. Then we know that the net force is zero. Example that we've used before is holding a front plank. If I'm holding a front plank there, I am producing force with my abdominal muscles to keep my torso in the air. Okay? The force of gravity is trying to bring me down to the ground, but my ab muscles are pushing or are creating a force upwards to prevent my body from going to the ground. So basically, the force of my ab muscles cancels out the force of gravity there. So we know the net forces in this system here would be zero. So forces are being applied, there just is no acceleration that's happening. So when we look at forces there, we need to think about the different components of a force. And typically, in our perspective, we're typically looking at two different components. We're looking at a horizontal component of force, and then we're looking at a vertical component of force. Now, this horizontal component, we can think about like left and right, but we can also think about how forward and backwards that force component is. Okay, but a lot of times we just simplify horizontal component in a 2D format, looking just left and right. And we could use trigonometric equations there to solve for force resolution. Again, that's not going to be heavily tested on here in this course here, but just understand we can use trig functions there to solve for this force resolution. Now, it's important that even when one of these, either the vertical force component or the horizontal force component, if one doesn't necessarily contribute to the particular system there, we must acknowledge both components there, and we should understand why maybe we are not including one of those different force components. And again, you'll see an example of this later on here in the course. So why do we need to think about these various horizontal and vertical components of force? Okay, it helps us to understand various different things that occur. Okay, one of these examples there is that why is it slower to run the curve of a track than it is to run these straightaways? And here's why. On a straightaway, okay, all the forces are going in one particular direction, moving you forward in a straight line there. Versus on the curves, some of the force goes straight, but some of the force pushes you to the center. Okay, so here's an example here. So I'm a runner here, okay, and I am going around this curve here, and I want to go in this black arrow direction, this force vector. Okay, so in order to go in this direction here, okay, I am creating force in this blue direction here, but there's some forces that are pulling me in there. Okay, and the reason I am pushing in with some of these forces because if I didn't push in with some of these forces towards the center of the circle here, what happens is it would fly off to the side. So therefore, some of the force I'm producing not only has to go forward, but it also has to go towards the middle. Okay, and what results here, okay, is this black resultant vector, this resultant force. Okay? So essentially, what happens there is it allows me to go around the curve there, but because not all the force is going in one direction, some of it, as you can see, is going towards the middle of the circle there, this causes you to go slower than if you were on a straightaway. And we can consider all these horizontal and vertical force components there using the tail to tip or parallelogram diagram. And while we're not going to harp on this a whole lot during the course here, asking you to create a ton of tail to tip or parallelograms there, it's important to understand the concepts of it. So here's one example of the tail to tip diagram there. So f of x here is my horizontal component. So I produce some sort of horizontal component, okay, and some sort of vertical force component, okay, and that results in a force component of going here in the upward direction. An example of this might be throwing a ball into the air there, okay. So I throw it in produce some force horizontally, some force vertically, leading to an upward trajectory of that ball that I'm throwing. If I was calculating that tail to tip thing, okay, I could also look at it going up first with the vertical component and then going to the right there with my horizontal component. But essentially, going from the tail of one vector to the tip of the other and adding to that there the tail of one of the vectors and going to the tip of the other, that can create a resultant force or resultant vector. Another way we could go about it is the parallelogram idea. And I'll start with these on the bottom because it might help make a little more sense. Essentially, you put all the tails together, then you look at all the tips and draw these imaginary lines, okay? And where those imaginary lines meet there, yeah, that would be considered your resultant vector. Here's another example of it where we're not going straight up horizontally or straight up vertically there, okay? But essentially the same idea occurs there. This one looks a lot more like a traditional parallelogram that you might see. Okay? And here's another example of that. That's, again, all the tails are together, okay? And you match the tips there, okay? Where they meet there would be where that resultant force vector would be. Now let's talk about motion here. So motion is essentially just the way that we change positions there. Okay? And for us to change positions there, we need to have two different requirements for motion to occur. Number one, we've got to have some sort of space to move in because the change in position requires space. Number two, we need to consider is that the time in which it takes for us to move. Okay? And this can be classified in three different ways. Okay? We can look at linear motion, we can look at angular motion, and we can look at general motion, both linear and angular. And again, we'll talk about that in the coming slides here. So linear motion occurs when all the points on an object move in the same distance, the same direction, at the same time. Okay? This is also known as translation. So you see translation there, okay, that's referring to linear motion. And we got two different types of translation. We've got rectilinear translation, and we got curvilinear translation. And so rectilinear translation is the direction of motion and orientation of the object does not change, and at all points travel the same distance. A good example of this is the 100-meter dash there. Okay? So when I run the 100-meter dash, I'm facing the same way, okay? And I'm moving the same direction, okay? And all the points in my body there, okay, ultimately travel that same distance there. Another type of linear motion is curvilinear translation. You might think that this is not linear motion because you got curve, okay, curvy referring to a curve there, okay? But curvilinear translation is also considered linear motion. What this happens here is the orientation of the object does not change, and all points travel the same distance, but the direction of motion does change, essentially traveling in a curved path. Common example, this would be running around the curve of a track. That would be an example of curvilinear translation. Now, second type of motion, there is angular motion. This occurs when all points of an object move in a circle, okay, or parts of a circle called arcs there, around the same axis of rotation. And this axis of rotation can be internal or external to the object. And on top here is an example of a person, okay, moving around an axis of rotation that is outside of that person. So as this person's performing this flip here in the air, okay, where my pointer is at right now, okay, this is where the axis of rotation would be. Notice that this axis of rotation there is outside of the body, okay, but the person is flipping around this axis of rotation there, okay, outside of the body. Below here, a figure skater spinning, okay, we got that longitudinal axis of rotation. This one's going through the center of the body there, okay, causing that person to spin very quickly. We oftentimes will refer to angular motion as rotary motion or rotation. Now, general motion, think of it as a combination of linear and angular motion, okay? And the nice thing about angular motion is that even though angular motion moves in circles or arcs there, angular motions can be combined to produce linear motions, okay? And typically general motion is the most common type of motion in the human body there. Okay? Here's an example, okay? When I am biking there, okay, upper body shows linear motion. So the upper body here is staying relatively still, so all points are moving in the same direction there, okay? So biking an example of general motion there. But legs are showing angular motion. If you look at the axis of rotation, essentially the knee joint there, okay, every time the person pedals there, okay, that knee joint is going to collapse in on itself and then extend, collapse and extend, moving in an arc. Okay, and so since the knee joint is moving in an arc there, that'd be an example of angular motion. Same thing happens as I'm biking at the hips and ankles as well. Hips and ankles moving in arcs or angles there, helping the body propel in a linear fashion. So the legs are moving through angular motion. So position here. So and for us to be able to move in space, we need to understand what our position is, okay? And position is just a location in space. And typically we use this using the Cartesian coordinate system, essentially the XY axis or X, Y, and Z axes there. And with these visual 2D or three-dimensional representations there, we always start with a fixed point, okay, called the origin. Okay, you can choose wherever this origin is going to be at depending on your particular situation that you're analyzing there. Okay, oftentimes we'll think about it in terms of where do you start. Okay? In 2 dimensions, okay, we've got a horizontal axis, oftentimes referred to as the x-axis, and one will be considered a vertical axis, otherwise known as the y-axis. And we can determine what position that person or object is on the xy axis, denoting a point xy, where x is one number and y is another number. Could be positive, negative, or zero. In 3 dimensions, we've got 2 horizontal axes of rotation, or axes, I should say. The x-axis, which typically goes left and right, and the z-axis, which goes front and back. And then our vertical axis is considered to be y. And so in 3 dimensions, we need to know 3 different aspects of position. We can denote that as 3 different numbers: left and right number, up and down number, and forward and back number. Here's a visual representation trying to show the x, y, and z axis looking at a 3-dimensional position. So where this black dot is, okay, this black dot here is 3 units or 3 meters to the right. It is considered 2 meters up and 4 meters forward. And that's the position there of that black dot. Where the x, y, and z axes meet, okay, where all the tips or the tails there of the different arrows there, that's considered the origin. Okay, so origin oftentimes will be where they started. This 0.324 would be where they finished. Again, 3 meters to the right, 2 meters up, and 4 meters forward. So a visual representation of position. So when we look at these, the x, y, and z axes, okay, traditionally the x-axis is going to be positive going to the right. Okay, so going to the right there, the x number would continue to get larger and larger and larger and more positive. Y-axis moving up would get more and more and more positive. The z-axis would be traditionally positive forward. And oftentimes, if we want to kind of figure out a way to help kind of remember it, let's think about the x, y, and z axes in terms of the right-hand rule. So the thumb, okay, points along the x-axis, and it points where x is positive, going to the right. My right pointer finger is going up there, and that shows where the y-axis is going to be positive. And then my middle finger is going to point forward, okay, knowing where the z-axis is going to be positive, which is going to be forward there. So again, just kind of the right-hand rule helps us remember there where the x, y, and z axes will be positive. Now, as we move in space there, we need to understand the difference between distance and displacement. Distance is going to be that entire path traveled from your initial position to your final position. And for distance is going to be considered a scalar quantity, okay? Meaning we only refer to how far that person traveled there, okay? Looking at magnitude only. Versus displacement there is going to be the straight line distance from the initial to the final position, okay? So understand that one of the big differences between distance and displacement is distance is the entire path traveled, versus displacement is that straight line distance. And since we're worried about a straight line distance, we consider this a vector quantity, okay? Remembering those arrows from previously, okay? So that's kind of what we think about displacement. Displacement is that arrow there, versus distance is going to be something a little bit different. Okay? A vector quantity for displacement there means that displacement has both a magnitude, okay? So how far that person travels, and a direction as well. Yeah. You can click this link here, okay, to show Marcus Allen there running in the Super Bowl. And in this play here, it says that he traveled 74 yards. Was that 74 yards in this video his distance or displacement? Pause the video right now if you want to take a look at that. When you're done, you can come on back. So here's a diagram of another person running there. Okay? And this kind of helps you better understand the difference between distance and displacement. Okay? So this dashed line path is what the player actually ran. So notice the player cuts back and forth there. Okay? And eventually there gets tackled right here. So with this entire path that the person traveled, that would be considered your distance. Okay? However far this is, okay, that is distance. Versus displacement is a straight line vector, okay, going from point where they started to where they finished. Okay. we again could refer this to as the resultant displacement or the resultant vector. So notice here the difference. Distance here travels a lot farther there than displacement, because displacement is that straight line path versus distance is going to be the entire path moved. So depending on the sports situation there, we might use distance in some situations or displacement in the other. Okay? Here's an example in track and field. Think about it for a second. Which would you choose, distance or displacement, for all your throwing events, long jump, and the 100-meter dash? Now compare that to which would you choose for the high jump, pole vault, and the 400-meter dash. For throws, long jump, and the 100-meter dash there, displacement would probably be better, and here's why. So if I'm throwing the shot put, okay, it doesn't matter how high up in the air that shot put goes or how low of a trajectory in the air that shot put goes. Okay, all we care about is how far that shot put travels in a horizontal path. That's what's actually measured. Same thing with the long jump there. Doesn't matter how high up you jump in the air or how low up in the air you jump. All that matters is how far you travel. Same thing with the 100-meter dash there. I'm going from point A to point B, so that horizontal displacement there, that's what would matter. So in this case here, okay, distance would not be as important. In fact, we would rather look at displacement for throws, long jump, and the 100-meter dash. However, if we're looking at high jump, pole vault there, this requires a running start, okay? But then you've got to go up and over a bar, okay? So here is where the path traveled in the air is a bigger deal. Because with that path traveling in the air, there's a bigger deal. I need to figure out at what trajectory angle do I need to launch myself off the ground so they go through the air and over the bar. Okay? So in the high jump and pole vault cases, okay, this is where distance would be better. So displacement better for these top three. Displacement would be better here. Likewise for the 400-meter dash, okay, this one, okay, this would be more important for distance as well, because for the 400-meter dash, I start in the same place that I finish around the track. So if I just looked at displacement and after running the 400 meters, I only would have traveled 0 meters, because where I started and where I stopped was the same location. However, distance, okay, this would follow my entire path around the curve, okay, and around both straightaways there. And that would account for the entire position traveled there. So for these bottom three, let me review here in case it wasn't clear. Distance is going to be more important for high jump, pole vault, and 400-meter dash to monitor, versus displacement will be better for your throws, long jump, and the 100-meter dash in track and field. Now we use distance and displacement in these next two terms, speed and velocity. And in common language, we'll typically look at speed and velocity meaning the same things, but they actually have some slight differences. Okay? So speed is the rate of motion, okay, versus velocity is a rate of displacement. Okay? And so with that there, okay, speed, if you take a look at, okay, speed essentially is the amount of distance over the change in time. So a triangle means change in, okay? T refers to time there. So speed is distance over time versus velocity is displacement. D stands for displacement there over a change in time. So two different terms, distance versus displacement. Okay? So just like distance there was a scalar quantity, speed would be considered a scalar quantity, versus velocity, because it refers to displacement, velocity would be a vector quantity, essentially the rate of displacement, and speed would be the rate of motion. Both these terms here, speed versus velocity, oftentimes use the same base units, which typically is going to be meters divided by seconds. Again, I'm not going to ask you on a test here to calculate speed and velocity, but for those of you especially a little bit more mathematically minded there, it might help you understand the difference between speed and velocity. Now we can look at average speed versus instantaneous speed. And so what average speed is you just take the total amount of distance traveled there and divide it by the amount of time it took to travel that distance. So if a sprinter runs the 100-meter dash in 10.8 seconds, we could figure out the average speed that this person ran at by taking the distance there, 100 meters, and divide it by the time it took to run 100 meters, which is 10.8 seconds, giving you an average speed of 9.26 meters per second. Now, instantaneous speed is looking at speed at a specific instance in time. And we can find instantaneous speed there, okay, by calculating the average speed as well. But what's important to understand with the instantaneous speed is that we typically look at instantaneous speed over a much smaller period of time. One example of this is that we could look at how fast was the runner running between the 40-meter mark and the 50-meter mark in that 100-meter dash. So if it took that runner 0.98 seconds to run between the 40-meter mark and the 50-meter mark, we could take the difference in that distance there, which is going to be 10 meters, and divide that by the amount of time it took, 0.98 seconds, gives us an instantaneous speed of 10.2 meters per second. So instantaneous speed is oftentimes useful where we're not necessarily, or we want to look at what speed at one specific point in time versus average speed, looking at what your speed is going to be over a longer period of time. So what do we use, speed, or what do we look at more, velocity? If the activity is in a straight line, it doesn't matter whether we're looking at speed or velocity, because speed and velocity will have the same value, because distance in a straight line is the same as displacement, because displacement is already a straight line. However, if the activity has changes in direction, understand that speed and velocity will no longer be the same, because speed refers to that entire path traveled versus velocity looks at the straight line path traveled. So speed may stay the same there, but velocity there would decrease. So if we've got velocity and we've got speed there, we need to look at acceleration, okay? Because what acceleration is going to be is the change in velocity. Okay? And since we're looking at velocity again, which looks at displacement, okay, we consider acceleration a vector quantity. Typical units there are going to be meters divided by seconds again. Or you could simplify that to meters divided by seconds squared. And just like we could calculate average speed and average velocity, we can find average acceleration as well as instantaneous acceleration. Now, since acceleration is a vector quantity, okay, acceleration can either be positive or negative. And now, while people might use the term deceleration to refer to slowing down and acceleration to speeding up, essentially we need to understand there that in the scientific literature, acceleration is also slowing down as well. So acceleration is the term that refers to speeding up and slowing down. Okay, deceleration is typically not used in the literature; it's used in more common language. Also understand here with acceleration, the direction of motion does not indicate the direction of the acceleration. We'll see that in a coming slide there. If there's no change in velocity, okay, understand that acceleration equals 0. So if a person is maintaining the same velocity, so essentially running at, like, let's say, for example, running at 5 meters per second there, okay? And they maintain that 5 meters per second pace. Okay? Since there's no change in velocity, okay, acceleration would be 0. Likewise, if velocity was 0, okay, acceleration also be 0, because velocity of 0 means the object's not actually moving. So here's a diagram here, okay? And let's take a look at direction there, okay? Looking at positive and negative. Essentially looking at your x-axis there. So if we're facing the right direction there, okay, whether we're speeding up, not changing speeds, or slowing down there, okay, as long as we're going to our path is traveling to the right there, velocity could be considered positive. If we were facing to the left there, okay, speeding up, maintaining speed, or maintaining velocity, I apologize. So speeding up, or velocitying up, maintaining velocity, or slowing velocity down there, okay, that velocity we consider to be negative because it's going to the left. Now, the second column here is the change in motion, where they're saying speeding up is going to be positive, slowing down would be negative. So speeding up, positive, okay, maintaining, okay, constant velocity be 0, okay, and then slowing down there, okay, that'd be considered negative. So speeding up, slowing down, or maintaining velocity, and slowing down. Now, A here, the direction of the acceleration, okay, so as I'm speeding up going to the right, acceleration will be going to the right as well, so it would be positive. Okay. If I'm maintaining my same velocity, acceleration will be 0 because I'm not speeding up or slowing down. However, when I'm slowing down here, okay, my acceleration, okay, is moving in the left direction, okay, because I'm slowing down there, okay, so my direction acceleration would be negative, okay, going the opposite direction. Now, if I'm moving to the left there, okay, yes, my velocity will be negative there, okay, but I'm speeding up going in the negative direction, so my direction of acceleration will be negative as well. Not changing there, constant velocity, so direction of acceleration will be 0. And then slowing down there, okay, I am slowing down in the negative direction, okay, so that means acceleration would be positive. Again, it's kind of wordy there, and it might be a little more difficult to understand, but just use this diagram, okay, kind of as a summary there of velocity and acceleration and how it compares speeding up and slowing down depending on the way that you are facing. So with acceleration there, the way we could calculate acceleration, since it's a change in velocity over a change in time there, okay, well, the way you could look at it is your final velocity subtracted by your initial velocity divided by your change in time. Okay. So again, we're not going to harp a whole lot on actually calculating acceleration on a test or something like that there, but it's good to understand for those of you who are more mathematically minded, what acceleration looks like and how we could calculate it. As a reminder before, in order we must have a net force there to be an acceleration. So if net force is 0, acceleration is 0. But if the net force is positive or negative, okay, there will be an acceleration happening. And we just saw that there in this previous slide.